Good morning. My name is Verónica Bolón-Canedo. First of all, thank you very much for the opportunity of being a speaker in this amazing conference. I come from the University of A Coruña in Spain, and my talk is about feature selection for big data, advances and challenges. I started working on feature selection in 2008 when I was about to graduate, and I needed to do a research project, so I joined my research group, Lydia, and I started working on a data set called KDD-CAP99. This data set had 41 features, and at that time we thought that there were a lot of features. So we tried to apply feature selection methods. It worked, and I continued working on feature selection. My whole PhD thesis was about feature selection, and until today. In these years, I've seen how feature selection had to adapt to the new challenges brought by big data, so today I'm talking about this. Okay, we're in a conference about big data. I know that all of you know about this thing with the 3 Bs. Okay, clicker. Oh, 5 Bs. Then we move to 7 Bs. If you keep searching, you have 10 Bs. They can be these 10 Bs or another 10 Bs. I found several ones. It looks like everybody wants to add his or her own V, and me too. Hello? Okay, I could add variables. I prefer features, but feature doesn't start with V, so I put variables. Okay, variables are very important. Sometimes we don't realize, but variables or features define how good our data is. And we need good data, data of big quality, to construct good models. So I think that variables deserve more attention. Maybe some of you are thinking that, for example, variables can be included in validity or visualization, even in volume. Okay, but I insist. I think that variables deserve its own V. Okay, so many people think that the more data, the better, because data is power. So we are gathering all the data we can. But this is not true when talking about features, features because of the course of dimensionality. This expression was coined back in 1952 or 57 by Richard Bellman. At that time, they didn't have big data, I can tell you, but they were worried about that maybe having a lot of features is not good, because if the features are not good enough, they can confuse the classifier or prediction model we will use afterwards. So it's better to use a dimensionality reduction technique. And some of these dimensionality reduction techniques is feature selection. Feature selection can be defined as the process of selecting the relevant features and discarding the irrelevant and redundant ones. I mean, it's like saying this feature yes, this feature no. We are keeping the original features. I insist on this because in my screen, I see the correct slide, I can tell you. Okay. So I'm not talking about feature extraction. Feature extraction is a good technique. I don't like it, but it's useful for sampling image processing, and I use it sometimes. If I need to visualize something in 2D, I can use a PCA, that's fine. But I don't like that feature extraction doesn't keep the original meaning of the features. So for machine learning, I think that it's better to use a feature selection technique. And what is a relevant feature? I borrowed this example from my postdoc supervisor, Gavin Brown. I like this example. Imagine that you are trying to guess the price of a car. So what features are relevant? For example, the engine size, age, mileage, presence of rust, etc. Are relevant. Color of windscreen wipers, the size of the stickers on windows, etc. And there are also some features that can be redundant, like age and mileage, so you don't need all of them. And why using feature selection? Feature selection has multiple benefits. The most obvious one is general data reduction, because if we reduce the data, if our data now is narrower, Of course, we limit the storage requirements. And then, if we apply a classification or prediction algorithm afterwards, we will increase the algorithm speed. Moreover, if we reduce the number of features, we don't have to collect irrelevant features in next rounds of data collection. Believe it or not, sometimes we can improve the performance. When we apply feature selection, we are happy if we just maintain the performance, but sometimes there is a nice surprise, and we can even improve the prediction or classification performance because we got rid of those relevance that were confusing the classifier. And finally, and as I said before, it's good for data understanding. Imagine that you are working with biomedical data, genes related with some disease or something. You apply feature selection, and you can tell the expert that this gene is related with this disease, and that gene is not. So that's good for data understanding. There are a lot of feature selection methods in the literature. We have new methods every year. Sorry. Feature selection methods can be classified into subset methods if they return a subset of the original features, or ranker if they rank all the features, and then you need to establish a threshold. According to the relationship with the classifier, we can have filters. They are independent of the classifiers, or embedded unwrappers that use a classifier, but they used to give better results, but at the expense of a higher computational cost. And also, they can be divided into univariate if they only consider the relevance of a given feature with the class, or multivariate if they take into account correlations between features. The bad news is that there is not the best feature selection method, so it depends on the problem, and sometimes you have to try several of them to find the best one for a given problem. So feature selection is successful because we prefer data quality over data quantity, and it has been applied on many, many, many different applications. Just to give some samples in biomedicine, facial recognition, in text recognition, because words can be seen as features, intrusion detection. This KDD-CAP99 dataset I started working with was about intrusion detection. Medical applications, very useful. Image classifications, classification, finance, almost every application you can think of. And if you want to know more about feature selection, here you can see an example with 4 books. My favorite one is the last one. You know, I really like the first author. I don't know if you can see her name. Just kidding, but there are lots of books, research articles, information on Google. And also, if you have questions, you can send me a message, and I will be happy to help if I can. OK, so feature selection was good, was being useful in kind of a comfort zone, but then we had big data. And big data brought a lot of challenges. These challenges can be seen as a burden or as new opportunities for researchers. I prefer to see them as new opportunities, and I will talk about that on the next slides. OK. In the same way as big data, we have now big dimensionality, because we have data sets with millions of features now. Here, we can see an example in the UCI machine learning repository, a typical repository that machine learning researchers use to get data sets. In the 80s, the maximum dimensionality of the data was about 100. Then in the 90s, it grew until 1,500. And in 2000, it was more than 3 million. And this is nothing, because in the KDD-CAP competitions, for example, in 2010, they released a dataset with more than 29 million features. In 2012, with more than 54 million features. And look also at the number of samples. These datasets are really huge. They don't fit in memory, of course. So this is a new challenge we need to deal with, because feature selection methods were developed years ago, and they were not prepared to deal with such amount of data. So we need to scale up our feature selection algorithms. I know all of you know what scalability is. And the problem in feature selection is not that, oh, I have a very slow algorithm, I need to turn it into a fast one. No, it's, in most cases, my algorithm doesn't work, it cannot be applied, I need to turn it into a practical algorithm. We will be happy if we have good enough solutions as fast as possible and as efficiently as possible. Here is Here is a simple example, testing the scalability in terms of computational time. You know, scalability can be measured in computational time, accuracy, allocated memory, it depends. In this example, we have the computational time when increasing sample size and feature size in a toy sample, testing 4 different methods. And for example, here you can see that MRMR, which is a very popular feature selection method, has problems when increasing the number of features. So it's a good candidate to be scaled up. When scaling up, we need to focus on some issues. For example, model complexity. There are methods that can look simple, but they rely on complex subroutines or nonlinear methods, etc. So they are very difficult to scale up. It's different if we have a univariate or multivariate methods, because multivariate methods are more difficult to scale. The parameter tuning, sometimes a method is simple, but we need to tune hyperparameters, and we require lots of executions. Or if we want to perform statistical tests, we will need some executions, so scalability is tricky. And also stability, because sometimes a method can be applied with big data, but it becomes highly unstable, and that's not good. A possible solution to scale up our feature selection algorithms is to use distributed learning. This is a simple scheme or a distributed feature selection method. We have all our data together, and then we can partition the data into several nodes. So each node will have a subset of the data. It will have a partial result, and then we have to combine all those local results. Maybe here it looks easy, but it's not, because there are some issues we need to take account. For example, data is sometimes distributed in origin, so maybe there is a class that is only present on some nodes, and this is difficult for classification, privacy issues. Sometimes we cannot share data between nodes, and it will be more difficult to combine the local results. If we are in charge of the partition, we have to decide if we prefer to partition our data by features or by samples. Sometimes it depends on the problem, and sometimes depends on our choice. For example, the issue of overlap between partitions. If we allow a high overlap between the different partitions of the data, it will be easier to combine the results, but it's not efficient, because we are replicating data on different nodes. And if the overlap is too low, it will be very difficult to recover a final result. And how to aggregate partial results is very difficult, as we will see in the next slide. Here, we can see a toy sample. We had 1,000 features, and each feature was assigned a number between 0 and 1, meaning its relevance. So we built the full ranking of all the features according to this number, and we call that the ideal ranking. Then we distribute our 1,000 features into nodes, up to 1,000 nodes. On each node, we rank according to this relevance, the features, and we had partial ranks. We use a common function to aggregate ranks, and we calculated the difference between this aggregated rank and the ideal rank. Here, 1 is perfect match. And as you can see, okay, when having 1,000 features on 1,000 nodes, yes, we recovered the ideal ranking. But here, when you have 8,800 features and 100 nodes, which is a lot, we couldn't recover the ideal ranking. And why is that? Because of Jarrow's impossibility theorem that says that when having at least 2 rankers, in this case nodes, and at least 3 options to rank, in this case features, it's impossible to design an aggregation function that satisfies in a strong way a set of desirable conditions at once. And these desirable conditions are things like if every node ranks a feature over another, this will be like that in the final ranking, or there is no dictator, things like that. So it's very difficult to aggregate partial results. Anyway, you can do things. Here is an example I presented in the IJCNN conference this year. We distributed the rankings across different nodes. Then we applied a classifier to see if, despite of the fact that we couldn't recover the ideal ranking, the results were good enough, and well, they were. There were no statistical differences between distributing data and not distributing it. Also, we have more sophisticated tools to allow us to do a parallel feature selection, as all of you know, such as Hadoop MapReduce, Apache Spark, etc. We can also use a GPU to accelerate the feature selection calculations. But there is no much effort put on feature selection. Actually, if you check on the MLlib of Spark, which is a library for machine learning algorithms, there is no feature selection method, to the best of my knowledge. You can see PCA, but PCA is not feature selection, okay, as I said. So, well, feature selection methods are not in MLlib as of yet, but people is starting developing feature selection methods for Spark. For example, in my group, we developed an information theory-based feature selection framework for big data under Apache Spark with very good results. In the slide, you can see an example of parallelization of MRMR feature selection method. Of course, the times were reduced. And also, we have a work when we also accelerate MRMR using GPUs. Okay, another challenge we have is real-time processing. Batch processing, you know, we can collect all of our data and process it easily. We have time to do it, but nowadays we have a need of real-time processing. We don't want to wait for anything. This is extremely important in spam detection. Okay, I want to know if my computer is being attacked now, not tomorrow. In video image detection, of course, in portable devices. If I have a watch or something that is monitoring my vitals because I have diabetes or something, I need the alert right now. In computer-aided decision systems, because sometimes we have experiences, doctors don't want to wait for the results, etc. Many applications. A solution is to have an online feature selection method, and there are some attempts in the literature, but the problems I found were that sometimes they pre-select features as offline step, so it's not flexible, or sometimes, okay, they have an online feature selection method, but there is no subsequent online classification, so you are losing something. And some classifiers are not flexible with respect to the input feature, so they cannot be adapted to new features arriving, and it's difficult. What is the solution? To find flexible feature selection methods capable of modifying the selected subset of features as new samples arrive, and that can start working with an empty subspace of features. Also, in my group, we developed this simple solution to start with this online feature selection problem. It's a pipeline that includes online discretizer, then online feature selection method, and online classifier. They are simple methods like chi-square or k-means, but of course, more complex methods are more difficult to adapt to online learning. We had promising results, as you can see in the graphs. Precision and recall increase as new data arrives. And the percentage of features, well, at the beginning it was high, because if you have only 2 features, both are selected. But then it's stabilized until a good percentage of features selected, and it became stable as data arrived. Another thing I want to talk about is feature cost. And because this issue is sometimes overlooked, when applying feature selection, we only think on the relevance of the features, but sometimes the cost is also important. Or we have two relevant features, but it's better to choose the one less costly. There are many examples of feature cost in our world. For example, in medicine, it's not the same, the cost of an MRI as than the cost of a blood test. And not only the economic cost, but the discomfort for the patient is also very, very important. And we need to discover if there are some tests that are uncomfortable for the patient, and maybe they are not really necessary. In supercomputing, of course, the time is the real cost. And also, another example is zoometry of living animals, like cattle, is very risky. So the risk is also a cost we need to take into account. We developed a framework for cost-based feature selection. So we included a part in the evaluation function of a feature selection algorithm to take the cost into account. It has a lambda parameter, so you can control the importance of the cost, because sometimes it's very important to decrease this cost, and in other cases it's like, oh, it's nice if I can decrease the cost, but if not, don't worry. Here you can see an example, and the cost was significantly reduced, but the classification accuracy was, there were no significant changes. So that's a good result. And also we tried in a real case. This case was tear film lipid layer classification to detect a disease called evaporative dry eye disease or something like that. They had a CAD system, but it took more than 1 minute to give results, and the doctors were like, I don't want to wait so long. So we were refining the model to decrease this time, because it was necessary to extract some features from the image, and if we extract one feature or others, the time changed a lot. Well, at the end, in our final models, we applied our cost-based feature selection method, and you can see there that, for example, up with a high value of lambda, the time was reduced a lot, but the error was bad. On the contrary, with a low value of lambda, the error was the best, but the time increased a lot. But you can find always trade-off solutions, like the one in a rectangle, where you have an error that is not significantly worse than the best one, and the time was considerably reduced. Visualization and interpretability. Of course, the typical approach to visualize data is feature extraction, okay? But as I said, there is loss of interpretability, and a model is only as good as its features. So features play a very important role in model interpretability. There is a need for interpretability and transparency in feature selection and model creation processes, because we need tools that are interactive and allow us to interact with the model, changing the features that are selected or not. This is more important than ever, because we are witnessing a kind of digital Diogenes syndrome. Organizations are gathering all the data they can, but sometimes they don't do it in a meaningful way. And they gather data, but they want to see some results with this data. So we would like to evolve from a data-rich, knowledge-poor scenario to a data-rich, knowledge-rich scenario. There are only few tools for this visualization, playing with feature selection. I found this one, which is really nice, because you can visualize the features selected by different feature selection algorithms in different colors. You can play with them. You can change them. That's very nice, but this is a good opportunity for research, because we need more. And finally, I would like to talk about this challenge. What is big in big data? We always think of huge data sets, but sometimes it depends on the context. If we have a smartwatch or something, maybe a data set that is not so big becomes very big. So there is a new line of research because we have a new opportunity to develop feature selection methods in computational constrained platforms. My PhD student, Laura, who is there, is working on this, and she developed a feature selection method that has very good results using only 16 bits instead of 64. So this is a good opportunity also for feature selection researchers. And to end this talk, I have 2 take-home messages. If you have a problem and you have never considered applying feature selection, please give it a try, because it helps a lot. And if it doesn't, OK, forget it. But give it a try, OK? And if you are OK and you are interested with feature selection, you think like feature selection is good, there is a good opportunity for new lines of research, because big data brought us some challenges that need to be addressed. And that's it. Thank you very much for your attention.